What's up, everyone? Welcome to what's going to be sort of a code walkthrough for the code for the game and game engine that I've just released a video about. It's going to be highly informal and a little bit more sort of lecture style, but I thought it could be a little bit more interesting to just go through the code in a more slow pace and try and explain a lot of the design decisions and stuff like that I've made. So let's get started. We're just going to be going through all of the code on my own terminal, just like how I do when I work on it. And full transparency, I am working off of a little sort of not really a script, but an outline for this lecture, if you want to call it that. But it's very informal. I don't really have any solid plans for what I should be talking about. So anyway, let's crack open NeoVim and get started. So, a little bit about the structure, or not the structure, the technical details of the engine. It is written in C++, using a few libraries of support. If we take a look here, just these libraries in the back end, a few for rendering, a couple for math, one for window handling here. We've got some sound and just some more basic stuff for config file parsing. One for stack traces, because those are a pain to get in C++, but it's written in C++. I'm using make as the build system, and we'll be able to see it in here. It is using C++ 20. But with that out of the way, I think the first good spot to start here to get an idea of what the engine looks like. Oh, actually, I'll just run it first. That's maybe a good idea, so everyone can see what it looks like. I will just drag this window up here. This is what the game looks like today. So it's a little different than what I had in my video. You'll notice the font is different. Oh, and you might be able to hear that sound coming through the microphone. That's a footstep tester that I'm working with right now. But this is what we have right now. I think the only difference is that these dandelions kind of rotate a little bit. The font is different. Oh, I don't think I ever showed this little like crafting tester menu in the main video, but it's effectively the same if you've seen the main video that I've done. But this is what the engine can do. I mean, it is technically capable of a lot more. But before I move on to some sort of actual level design and stuff like that, this is where we're at. And so taking a look at the engine code, or just getting started, I'm actually going to get my outline up down here. Yeah, so I think the best place to start is probably in all of the global state that's kept in the engine. And I know you might be cringing at the idea of global state in some application, but honestly, I think in game dev, it's okay to, and probably many other applications, it's okay to use global state. You know, especially if I'm the only person who's, working on this code, controlling this code, you're not going to stop me from using just a massive struct of globals in my code, global systems and things like that. So let's get started with that. So you can see that I have, I'm not actually including headers for most of the subsystems in the global state here. They're just done through indirect raw pointers, or direct raw pointers. And you can see that, can I fit? Okay, I'm gonna zoom out a little bit so I can fit 2 columns of 80 lines on the screen. There we go. I hope everyone can still see that. But you can see here in the global struct that it basically contains all of the subsystems that are necessary to run the game. It's very simple. It has a couple of tick and update methods on it that will just perform some updating on the components contained in it. But this is where all of the game is contained effectively. Things are initialized in main, and they're done through this pointer system, so that global doesn't have to deal with the lifetimes of these objects or anything like that. Everything that exists on global exists for the lifetime of the application. As you would hope with some global state. And it's basically just run through in this whole, you can see in main, I have this whole just initialization list. where things are, of course, declared in the reverse order of how they need to be destructed for the game. But you can see we basically just initialize some system and stuff like that, and then hand control over to, where is it that we do that? To the game state, which is, a game state is just a state that implements some initialization, destruction, tick, render, update. Tick is my, I'm not sure how common this is, but tick is my name for the fixed update in the game. Update is my name for the every frame update, and then render, of course, renders. But these semicolons don't need to be here. Just gonna remove those. Yeah, and then that hands control over to the game state. So anyway, everything is contained in this global state that's declared in the main translation unit. You can see it declared and initialized here at runtime in the main translation unit. And that's basically how everything gets access to the renderer, to the platform, to timekeeping, to the UI, allocators, basically all the global state that's needed. And you can see it's used all over the place if we check out like something like this, for instance, this that controls entity camera following can just include the global header and then go through the global game state to get to the current game camera. Ideally, all of this stuff will be done by dependency injection and stuff like that if you're following true object-oriented dogma. But I think at some point, in the interest of speed of development and stuff like that, it just makes sense to include things as global state. And it's nice that our camera follow component doesn't need to keep some sort of weird reference to the global game camera that can eventually change, and it can just go through this global state. Anyway, though, that is the basic root of the project. That is the our big God object. And then a little bit as well about the general structure of the project. You can see I have my includes here, all going from the root directory. This is just my own personal style of things, but of doing things. But basically, we have in our source directory, we have some source and some header files, and then things are organized into there we go. And then things are organized into sub-modules that are everything about entities, everything about graphics, input, levels, items, and I don't really stray away from putting modules that include common code in the things that need to be shared across rendering, modeling, game code. Just directly into the source directory, because into the root of the source directory, because I don't, I'm not really going through and looking at it in a file manager. So it's fine when I can just make sure that I can search for things in NeoVim, and that works for me. Yeah. So going from there are basically three primary things. Primary elements in the game engine, and those are, as you can see in the global state here, those are tiles, which are the blocks that make up the map and everything. Items, which are, they're items, they're things that can be moved around in the inventory, and then entities. These item manager and tile manager are actually instances. Please ignore this template garbage. I promise I'll refactor it at some point. These item managers and tile managers that you can see on the global game state are both instances of component manager, and that as well is where is it? The entity manager that manages all sorts of entity types are also it's also an instance of this component manager, which is really I would say basically the core structure in the game. And what this basically implements is a generic entity component. I don't want to say system, because it doesn't deal with systems, but it just deals with effectively types of objects identified by an ID that can have different components that control their behavior. effectively an entity component system, but it doesn't implement any of those sorts of, it doesn't deal with systems, it just deals with components. Because as you'll see later, I don't really have a notion of a system in my code, but this is the what I would call the core structure and all of the engine. And this code just includes this just includes management for components, the component types, and everything. And well, if you look at a component, we can take for an example an entity component. That camera follow component is actually a good example that we were looking at. So, like a traditional ECS structure, entities, as well as tiles and items in this engine, are made up of, or entity types are made up of components. Entities are made up of components, sorry. Tile types and item types are also made up of components, but the important thing is that entity types are not made up of components, just entities themselves. That might be a little confusing, but I hope you'll get a better idea around it as I explain. But anyway, this camera follow component is, if we take a look at the player entity, so this is the code, I'll show you where we're using it. This is the code that will spawn a player into the game, this entity player create, which takes an empty entity with no components in it, and returns that same entity, hopefully, with all of the components added that make it a player. And you can see here it gets this camera follow component along with a bunch of other things, something that handles the player light, its health, stamina, the player being able to jump, it being able to take footsteps, it being able to interact with things. But this is an example of a simple component, this entity camera follow. And when you add the component to the entity, it's a subclass of this entity component, which is an instance of that this component from the component manager, space type. This will make it so that the camera follows the entity that has the camera follow component on it. You can see here as well there's some macro garbage. This is just used to make sure that all of the to handle the ID system in the component manager, because things get a little complex when you want to have types that are registered automatically from the translation unit at runtime. And then each type needs to get an ID that should ideally just be an integer or something like that, so that when you want to refer to components of a specific type, you just use that integer rather than hashing a string or something like that. Anyway, that's why there's all of this macro garbage everywhere. But this is how a simple component is introduced. And then you can see here we have all of the implementation for the component that basically just says that this entity component has some handlers for specific events, like when the entity position changes, when the camera rotates, every time there's a tick in the object, so that's that fixed update again. And that's basically the core of the engine, the core of how entities are added. And this is pretty normal. I think, there are plenty of games that use entity component systems. I know some larger game engines do as well. I think Unity does. I'm not sure about Unreal. I can actually delete this comment that was implemented. Really cleaning up the code through my lecture here. So this is pretty common to do with entities, but what I've also done is, if we take a look at tiles or blocks, is that this tile manager is also a component manager. So instead of going through this, like if you've ever dug through like a Minecraft clone or something like that, you'll probably notice that in the typical object-oriented structure of things, there will be like some sort of a base block type. And then that block type will have, it'll just be traditional object-oriented programming. That block type will have some subtypes that will, talk about like how, describe how slippery a block is and something like that. And it'll just be going through all of these virtual methods and everything. I didn't want to do that for this game. I've written plenty of things like that, plenty of systems like that with traditional object-oriented code. And I think it just gets messy. So I decided, in addition to applying that entity component way of doing things to entities, I would also do it with tiles and items. So, you can look just like those entities, get the camera follow component if the camera needs to follow them. You can look at, yeah, maybe that's a good example. TCAABB. AABB is an axis-aligned bounding box. You can look at TCAABB for all tiles that need to have a bounding box around them. So all tiles that maybe also have a collision component, which can also describe, if a tile needs to collide with things and how it does that. Those of you that are maybe more familiar with C++ and entity component systems might notice that my components include virtual methods in them. And you might say, oh, that's probably bad for caching. Yeah, but this is also more of this is more of an organizational thing than a performance thing. I'm not doing an entity component architecture for everything out of performance concerns, but more just out of code organization concerns and having just massive classes that manage tiles and items and entities. And so we can also take a look at, for example, item components. So all items typically have sprites, and those are described by this item sprite component, for example. So you can basically see how this component architecture lets us, what's a good word for it, compartmentalize behavior for items, for tiles, for entities into their own sorts of objects and code that sits ideally separately from all of the other code that describes things that items, entities, and tiles can do. Yeah, and those systems, their names are item.hpp, tile.hpp, and entity.hpp that manage these, that describe these component manager structs. Those are all included in the global state. This tile manager that manages tiles, item manager that manages items, and this entity type manager is something else. We won't look at that right now. The entity manager, or the ECS, actually sits on the, I believe it sits on the, it sits on the level, actually, no, it sits on the game state, sorry. It does exist as a unique pointer on the game state. Because entities might need to move between levels and stuff like that. But anyway. Oh, and also an important thing of this entity component architecture is that all of the entities and tiles and items that you pass around, rather than being like terrible, awful, maybe dangling pointers or shared pointers or whatever that you're throwing around and keeping maybe in different places in your code, they are just really, really thin wrappers for an integer and a pointer. The pointer points to the thing that manages them, and the integer is just their ID. And then through that, you can get all of the potential components that you would want to get if you have an entity, a tile, or an item. And so in practice, you might be wondering how this actually looks to use. And a good example here might be, I just kind of want to try and find something that's going to use multiple components. Maybe like we can take a look at this, for example. This is code that will attempt to drop the currently held item. It's in EC control, which stands for the entity control component, which is the thing that does a keyboard interaction for entities, which could theoretically be added to any entity. In practice, it is only on the player, but this handles an entity with an EC with a control component that wants to drop the currently held item. So what we do is we use this entity, which again is just that thin ID and pointer, and then it has all of these. Oh, there is something broken in my NeoVim. Maybe it has all of these. Functions, methods on it. They're not methods. None of them are actually virtual. They're functions. Procedures, maybe, that are available on it, where we can get, for example, it's, as you can see down here, we do with an EC inventory component, but that gets an optional component. But gets, let's say, EC inventory. And then this, if we look at it, auto component, we can check the type of this, and it's a reference to the EC inventory component, because also through Git, we're implicitly asserting that that component exists, otherwise the thing is going to crash. We can also do opt, which if you look at the definition of this, will return an optional pointer to an inventory component. So we get an optional reference to the inventory, or a pointer to the inventory component, which is what we're doing here when we want to drop something. We assert or return. That's this opt-or-ret macro. You know, I still use macros all over in a lot of places in my code. You know, you can take a C programmer out of C, but you can't take the C out of the C programmer. I'm going to keep using macros because they make my code cleaner in a lot of places. Anyway, we get optional an optional inventory component, an optional item hold component. So any entity that can hold an item will have this item hold component. Any entity that has an inventory will have this inventory component. We assert that they exist. Then we get the off of the item that the item hold component says it's holding, maybe because this held function returns an optional item stack, an optional pointer to an item stack, which may or may not exist because we may or may not be holding something. We use this opt-or-ret macro again. That's like option, either dereference the option and try and get out of the option what's in it, or just return from the current function. And then once we have all of those components, and we're sure that we have them because otherwise we would have just returned out of the function, we spawn a new entity item instance, and we say that we want to drop from this entity. So we give it an entity and the item stack that we're dropping. That gets removed out of the inventory component. And this is how a lot of the game code ends up looking in practice, is just really what I would call clean, just, you know, check if we have this component, check if we have this component, check if we have this component. Okay, fantastic. That means we can do this with all of these different components, use them, get out of here, get out of this function. Which I think leads to really granular, really readable, really understandable code compared to plenty of other games that I've written. And this is how it works for, you can see that we get an item component off of, or actually we don't get an item component off of it. But in theory, we could also, now that we have this this held item, we could do held item.get sprite. Oh, well, I would need to import it, but anyway, and then we could probably render it or whatever if we really wanted to in here. But everything is just interacting through these components. Yeah, and that's the basic. That is the core of the system. There's also some more stuff to talk about, maybe with the way entities work, and this. If we look at the position again, there are also events that go alongside entity components. So any component can emit event on an entity or emit events to all entities. And then components can optionally choose to respond to those events. So we go back to camera follow. We can see that here, when the type is registered from this macro, we're adding these handlers that, and this is a maybe nasty template, depending on how you look at it. That basically will take a look at this position change function, which we can see the signature of here, and see that it takes a position change event as a parameter, which is an event that's emitted by the position component that says the entity position has changed. And then this EC camera component has decided, okay, well, I'm trying to get the camera to follow the current entity. I probably need to know whenever the current entity's position has changed. And then so it registers itself as wanting to respond to this position change event every time there's one emitted. You can see it also does it with tick, fit entity camera, the camera following needs a fixed update on it as well. And then if we go to this, Oh, well, position change actually doesn't do anything right now. But tick, for example, every time there's a fixed update and there is a fixed update event emitted, we want to follow the entity. Or, for example, every time the camera is rotated around, we need to snap the camera to the new position rather than doing a soft follow. And these events are used all over the place. If we look at what's another good example? Position, for example, responds to its own events. It's got a tile change event, chunk change event, position change event. And these are also declared through some maybe evil macros, depending on how you look at it. And then you can see that the position component up here responds to its own position change event, because that's just a convenient way about scheduling things. But and when the position changes, it says that it has it registers that the change happened on this tick. And then there are also destroy, initialization, and destruction events that handle initialization and destruction order and stuff like that. You can see in here it just removes the entity out of the current chunk. And that's maybe a good segue into just a really brief overview about how level data is managed. Everything is contained in this level, which is made up of chunks over here, which contain as their base data type. Yeah, they're basically just a 3D array of this chunk data is a wrapper for an unsigned 64-bit integer, and that contains all of the tile data and stuff in the world. And then you can see that's divided up through these fancy data access wrappers into tile data, lighting data, which actually might be removed, hit points for the tile, subtile data if we need to divide the tile into smaller tiles, for example. And that's effectively how level data gets organized. And then so that's basically all of the game code, effectively. And how it works and how it interacts with other systems in the game. So next up, I kind of want to pivot and take a look at because I know a lot of what I've been focusing on my latest videos have been rendering, and how because that's honestly probably the largest component of this engine, this game that I've been working on. I'm just going to drag up the window here. Is rendering and getting everything to look like a game and look the way that I want it to. So everything there is managed in the renderer, of course, as you might expect. So the renderer, again, almost like global state, is just it's got some resources on it, but it's effectively just made up of a bunch of different subsystems. Like we have a sprite renderer, a particle renderer, an icon renderer, the font renderer, and that's wrapped around a bunch of other code that handles compositing and stuff like that. So taking a look at this and the way this works, it's quite BGFX specific. So again, BGFX is that the rendering library that I'm using. Normally, I might want to abstract a little bit more over any sort of rendering backend that I'm using, but BGFX is in and of itself that abstraction. So it's quite tightly coupled to BGFX. But basically, it's just the renderer is just a huge collection of subsystems that handle, for example, sprite rendering. If we take a look at this one, this will just render a batch of sprites, effectively. A big list of these texture, position, color, alpha value things. And it's effectively what all of these are. Sitting under that, of course, as well, we have all of the things that manage different, they manage frame buffers, that manage textures and things like that on the renderer here. And this is, honestly, mostly just behind the renderer to support it. It's mostly just a whole bunch of boilerplate code. I have if we look at frame buffer, for example, it is just a thin wrapper for this this BGFX frame buffer handle, because I wanted to make things maybe a little bit nicer to work with for myself. Oh, that semicolon can also be deleted. Maybe just a little bit nicer to work with for myself. What's the word? Oh, that line can also be deleted. Maybe a little bit nicer to work with for myself, and maybe not just work with the raw BGFX objects all the time, especially if they're being exposed to places outside of the graphics module. So that's why I have a large abstraction over textures, for example, which we can actually take a look at now, because it's probably the largest component of rendering. So I don't think I've actually mentioned it in my video, but I handle textures in what I think is a pretty unique way. All of the textures in the engine exist on one massive mega texture, and there's just one of these. It's just one huge automatically managed texture atlas. It actually doesn't live on out of convenience, it doesn't live on the renderer. It lives on global state, but and this massive texture atlas, because the textures are so low resolution, everything is pixelated, we can basically just manage, just use one texture for everything in the scene and everything the game could potentially want to render. I think with everything I currently have in there, and there are a bunch of dead textures that I'm not even using, I've filled maybe less than 0.002% of the maximum texture size that you could expect off of a platform. It's 8,192 by 8,192 pixels, I believe, right now. Oh, man, I'm fixing bugs all over the place. This should be marked explicit. But yeah, and that's basically how textures are managed. They are, and this also goes into resource management as well. So maybe this is better explained by how textures are actually used. So let's look at how textures are used by the dandelion. So if you remember, from the video, we had that dandelion texture, and that if we throw it up in preview here, this dandelion sprite sheet, it just looks like this. It's just a sheet of sprites that make up those 3D dandelion models. And then in terms of how that's used and loaded into that global texture atlas, we use these sprite sheet resources that live on each translation unit. So each like object file can load its own resources. I used to have the what I would say more like normal system of textures being loaded with some sort of name. Like for instance, this entity dandelion file being a texture file being loaded as entity_dandelion, and then everywhere you wanted to use it, you would go to some sort of global texture lookup, and then you would get the texture off of it by name, and then you would use it. But I found that added some sort of like extra layer of indirection almost, because I kept experiencing throughout development that like I changed the name of a texture or something like that, and then everywhere I used that texture name's that texture string entity_dandelion, the references just break, and then things fail at runtime. That's not so nice. So I decided to move to a system where resources are defined per translation unit. And you can see that's not even just textures. For example, we have this sprite sheet, which is that gives access to that dandelion sprite sheet that I just showed. But also the dandelion mesh is managed as a resource as well that lives on this. You can see it's model dandelion, so all of the dandelion rendering code that lives on this this model dandelion translation unit, which I find is a much nicer way to manage resources, because now you can't have a broken reference to this that will fail at runtime, a broken reference to this dandelion sprite sheet, because it's literally something that exists in the code. It is literally a variable in the code, which is super nice. And then so everywhere we want to use this, for example, I talked about maybe using it in practice. Well, actually, you don't even need to do the sprite sheet.get anymore. done some syntactic sugar and operator overloading to make that a little bit nicer. But you can see here the dandelion just gets that resource just gets used to load voxel models, make them out of the sprites there. And so it's a really simple system that doesn't involve, for example, doing this. So you can imagine in another world, pre this resource change, that we have const auto sprite is global renderer sprites entity dandelion or sprite sheet or whatever, and then we go through and we get all of these here. But that kind of sucks because what happens when in your your resources file or something like that, or God forbid you do something like this, entity dandelion. What happens when this texture is missing? Then you get a runtime crash. And it's fine because this model dandelion is maybe initialized at runtime, but what happens when in a rendering function you need to refer to some other texture that may or may not be loaded? That doesn't get called until like halfway through you're running the game, or maybe it gets called like very seldom. And then you just have this runtime crash. So a lot of my programming philosophy deals with making sure that crashes happen early, and that if things are going to crash, they're going to crash early. They're going to tell you why they crashed, because I think it's Jonathan Blow who said it in one of his the guy who made Braid and The Witness, who said it in one of his programming talks, that runtime crashes like null pointer dereferences and stuff like that aren't that bad. They aren't the worst kind of bug. The much worse kind of bug is a silent bug or something like that. And so you want to, I guess, just make sure that runtime crashes happen early, and they happen in a very easy to handle way. They're not some sort of nefarious bug where it's some dangling pointer or, for instance, some string reference that you don't discover isn't there until you're a long way through running the game. Anyway, that's my little resource management rant. But honestly, I've made that mistake plenty of times before with string references for resources. This was only something that I ended up doing later on in engine development because I was getting really tired of those string references. So anyway, everything is managed through these resources. You can see typically it's either going to be sprites or, even though it could theoretically be whatever, or meshes, thin wrapper for vertex and index buffers, or what I call a multi-mesh, which is a larger mesh buffer for multiple kinds of usually similar meshes. Like in this example for the dandelion, we have a multi-mesh that you can see gets everything, gets all of the different meshes for like the flower and the leaves and the stem of the dandelion added into it. This is just kind of for efficiency purposes, so that we make sure that we're not just creating thousands of small meshes, and every time we need to render a dandelion on the screen, we're going out to say, okay, now we need to render a petal, and now we need to render a stem, and now we need to render a dandelion, the flower. We just say, we're rendering a dandelion, the stem starts here in this mesh buffer, and the leaf starts here in this mesh buffer, and the flower starts here in this mesh buffer. Here are your matrices, go wild and render this. And those are basically the renderer resources. These are also tied, that was not intentional, tied to the lifetime of the renderer. You can see through this list of managed resources and a large comment over it explaining exactly what it is. These are tied to the lifetime of the renderer because obviously they need to be deallocated when the renderer goes away at the end of the program's lifetime. The last thing maybe that I want to talk about with the renderer here is something that I did talk about in the video, but I want to go a little bit more in depth with, and that's this sort of palettization that I'm doing, because I read earlier today someone wrote a comment about what's the word, how the palettization was worked and how I might want to move it out of RGB space. And I basically just wanted to say that the palette is managed as this 3D texture, and it may be just an interesting thing to point out. It doesn't really fit into this sort of lecture, but it's that all of the palette the palette colors are converted from RGB and then into this linear color space called CIE Lab, CIE-LAB. I don't know how you're supposed to say it out loud. At runtime, at render initialization, and then upload it as a 3D texture. Because when you're palletizing things, you want to be able to find the distance in a space that's not the distance between two colors to find out how close they are in a space that's not RGB, because RGB isn't so good with, I think it's something about how it corresponds to how the human eye sees near colors and stuff like that. But anyway, that's also handled in the render. I don't know how super relevant that was, but the most important thing maybe on the entire render, and I think the last thing I'll talk about here, is this composite function, which you can see gets called out of game state, or the game state, which basically at the end of every render cycle, it says to composite the current frame. It passes in a couple of lambdas with 3D rendering and 2D rendering, because the composite function might need to render multiple times, for example, for shadows and things like that. But yeah, this is basically just the big management of, or the big manager of how each frame gets rendered, making sure that all of the proper shaders are called, uniforms, shaders are used, uniforms are set, screen quads are rendered because it's a deferred renderer. Yeah, and that's basically the large overview of how everything gets rendered in the game. In practice, if you want to, for example, render, we can take a look at the player entity to look at an application of this maybe. Here we go. We see player render. So this is a render component that handles how the player gets rendered. So this render entity component just responds. Oh, that line can be removed. Just responds to a render event. Event responders can all event handlers can also be virtual as well. But it responds to a render event, and it basically, you can see this model manager is again, so modeling managing the player model, like that dandelion model. You saw how the dandelion model had resources in it, in its translation unit. The player model also has resources in it. Then the player model itself is also a renderer resource, because it needs to be attached to the lifetime of the renderer. And we basically just call into that and then render it. And this gets called at the top level by that composite function, to which we passed in a lambda that tells the level to render itself, that tells chunks to render themselves, that tells entities in chunks to render themselves. And then that's how we get all the way down here. And then in this render function, you can see this is where the rendering is actually happening, going into these models, into these meshes that you can see here, and then these actually tell BGFX to render vertex buffers and stuff like that. But that's how the whole thing is rendered. So we've got the rendering game logic. The next large system is maybe the UI, which I talked a little bit about in the video. So I don't know if there's too much more to. Sorry about that little recording issue there. So the next most important part to go over is probably the UI. This is, like I said in the video, your traditional object-oriented hierarchical UI structure, where basically, again, things can respond to, if we look at the root UI object, things can respond to update tick render as well. They get these sprite batches because, of course, all of the UI is going to be rendered in 2D. And then it's just handled as a hierarchical structure where everything is based off of this UI root, which is itself a container, which is itself a UI object. that manages the whole UI hierarchy and everything. It's not too complicated, and of course, because it's like a pixel art UI, it doesn't really handle um, resizing and stuff like that, which is also the reason why I kind of decided I wanted to roll my own UI library. But right now, it doesn't really have too much. I think we just have buttons don't even exist. I think the most complicated thing that we have is all the HUD elements, for instance, like the hotbar, the thing that shows the items on the bottom of the screen. And that's basically just, again, resources, rendering, basic control logic for scrolling and things like that. Yeah, and then I think that's probably everything that I want to cover about the UI. I think the last couple things that I'll maybe go through are just some more interesting stuff about how the game works on the back end in terms of memory allocation. So memory allocation is obviously in game development something you want to pay pretty close attention to. And most of the memory that's allocated at runtime, if it's not contained in some standard library container like a vector or a queue or something like that, things get allocated onto these bump allocators that live on global state. And if you don't know what a bump allocator is, it's a simple memory allocator that basically owns a large block of memory, you could say. And then if you ask it for 64 bytes, it has a pointer that points to some free memory, and then it increments the pointer by 64 bytes, and it gives you the pointer that you asked. It gives you the pointer to the start of that memory. Then the next time someone asks for memory, it will just increment the pointer again by the number of bytes they requested. And it's not garbage collected in any way. It's really fast to use. It's really fast to get memory, and it's fast to deallocate memory. And so you can see here we have two main memory allocators that are used here, which are the frame allocator, which is a bump allocator for all memory that needs to exist for the duration of the current frame. And then the tick allocator, which is the same thing. It's just operates on ticks. So every fixed update, you can allocate memory in this tick allocator, and you know that it's going to be cleared away at the start of the next tick. This long allocator is maybe a little bit more complicated, but that has to do with it. For some BGFX operations, for instance, when you request texture data from the GPU, you need to have memory that is like your destination buffer. You need to make sure that it exists for a set number of frames in the application. Or if you're sending data to BGFX, for example, you need to make sure that the data exists for at least 2 frames, so the GPU can read it, and then you can get rid of it. So similar idea here with the long allocator, but these are also just dead simple. What's the word? Dead simple bump allocators. It's a bump allocator that's made up of smaller bump allocators and blocks, and then what it does is if you have allocated a lot of memory at the end of a frame, then it will, where does that happen? Here, it will reallocate itself into 1 mega block. So for example, if you have one frame where you use 16 megabytes of memory, but it's split across 4 blocks, then for the next frame, it will say, okay, we're going to get rid of all these smaller blocks and just allocate one large block of 16 megabytes of memory, because if you needed 16 megabytes of memory this frame, you might need it next frame, and you're probably going to need it later on as well. There might be some some contraction mechanism later on, but so far these allocators don't use too much memory. Yeah, and so maybe the last thing to cover in terms of end instructions, stuff like that, is how utilities are managed, or at least it's the next thing in my outline. So if we look at that, because I know all game engines will end up with a lot of just like miscellaneous, like bundle functions and stuff like that. This was a big question for me as well when I was starting out learning C++. Exactly what can I jam in a header together? And I think this does go against a lot of what's the word, C++ ideology, C++ dogma. But I have jammed all of my standard library headers into this util slash std header. And it's fine. Everything works perfectly fine. The compiler can still deal with it. Yeah, and you can see that gets used. I think this std header and this types header, which contains aliases for all of the basic integer types, floating point types, and stuff like that, and then some more template stuff because it's all about types. Gets included basically everywhere. Like if we look at position, or maybe not position doesn't include it itself, but you can see everything needs access to types, everything needs access to standard library. And this is just so that, for example, I don't end up with a massive list of standard library headers on top of every file, because especially managing them in Vim and not using an IDE, things will get a little bit unruly in terms of include management. But I think that's basically the overview of how the engine works. I went through game code, I went through rendering, memory management. Yeah, and I think that's basically everything that I wanted to talk about. Yeah, so I think that's about everything I wanted to go through. That I hope that gives a more in-depth look into the game engine internals and what a project of this size, not that it's terribly large, of course, but what a project of this size written by one person actually looks like. What a homebrew game engine looks like inside. So, I hope you might have learned something. I hope you saw a bunch of my code and thought that it was garbage and are going to tell me in the comments that everything I'm doing is wrong. If you have any questions as well, throw them in the comments, and I will try to answer as many as I can. Also, if you're just wondering, for example, like things that I didn't go through, like how do you manage localization and stuff like that through this like locale type. Anything that you saw in the code, feel free to ask me about. Yeah, so thank you very much for watching. I hope that you enjoyed the video. I would like to maybe do more of these, also in maybe a bit more of a stream format. I know this one wasn't a live stream, but that's because I think trying to manage 600 people or whatever, however many people would come to watch, while I'm trying to give a sort of lecture style thing, might have been a little too much. So anyway, thank you very much for watching, and I'll see you in my next video.